topic yet. It's actually not your textbook. So I've got some problems for you on the worksheet when we're done. Solving exponential equations. I mean, so far in this course, we've solved like linear equations. Here's an example of a linear equation. Very simple one. We generally solve linear equations by doing what's called isolating the variable. That means getting x on its own, divide by 6, or divide by 2, x equals 6. We've also solved quadratic equations. Here's an example of a quadratic equation with an x squared in it. What are methods for solving quadratic equations? Factoring or quadratic formula. It's two methods. Set it to 0. It's very different than solving a linear equation. Finally, now we introduce a third type of equation, and I think the first thing you need to understand about solving equations, what type of equation you have, these are exponential equations. Can you tell just from looking at the first two examples what makes them exponential equations? Yeah, that's a perfect answer. The variable's in the exponent place. Okay, so we need a strategy for doing that as well. Now, as it turns out, the first two are set up very nicely. Okay, and we're only going to look at certain types of today where they kind of work out nicely. I'd like to point out this one. You can probably just get the answer by looking. Can you see from your power chart? 5, right? 2 to the power of 5 is 32. The answer is 5. Okay. A method of solving that we'll use this to explain a method. You can replace 32 with 2 to the power of 5. Since we know that 2 to the power of 5 is 32. If you don't know that yet, you're probably going to learn that by the end of next year. It's on your power chart as well, so it's there for you. And then we'll use this example to teach a lesson, and that is if two powers are equal and their bases are equal, then it must be the case that their exponents are equal as well. So I could say a little therefore x equals 5. The only way for two powers of base 2 to be the same is if their exponents are the same. Okay? It's not like on your powers chart, you had a power of 2 that was equal to 32, and you had some other power of 2 that was equal to 32. That's impossible. When you look at a row on your powers chart, they're all different numbers. Okay? So if they were the same, that would be the same. That helps us in this example right here. 3 to the power of 2r minus 1 equals 81. Okay? So for today's lesson, for today's solving exponential equations, the idea is we're going to try to make the base the same. Notice that the left is a power of 3, but 81 is what? 81's on your power chart, yeah? 3 to the power of 4. It's also 9 squared, but here it's 3 to the power of 4. And I have 3 to the power of 2r minus 1. Well, now you have two powers of 3 that are equal. The only way it's possible for two powers of 3 to be equal is if the exponents are equal as well. Now, some students like say, oh, you get to cancel out the 3's. No, you're not canceling out the 3's. You're just realizing that the exponents have to be the same. That's why I'm putting the little therefore statement there as well, to try to help you understand where I'm getting that from. Once we start crossing things out in math, we start making all sorts of mistakes. Crossing things out means you divide out or subtract out. In this case, you're not actually doing anything. You're just realizing the exponents have to be the same. And now it's a linear equation. 2r must equal 5, so r is 5 halves, or 2.5. I'm going to build up as we get a little bit more and more challenging. Yeah, we're going to try to make the base the same. Now, in today's examples, you'll always be able to do that. Obviously, that's not always going to be the case. Next year, you'll learn how to solve them even if the bases aren't the same, but the setup of the problem will still be the same. Okay, so it's the helpful thing to learn how to do anyways. All right, 16, 3y plus 1 equals 8 to the power of y. Now, this one's a little bit different because, I mean, there's no way to take 8 and make it a power of 16. Not easily, anyways. Okay, not easily. 8 squared is 64, 8 to the power of 1 is 8. But I noticed something about 16 and 8. They both have something in common. What does 16 and 8 have in common? They both divide by 8. That is true. That doesn't help us in this example because I can't really divide both sides by 8 because the exponent here. Okay? They're both divisible by 8. They actually share something even stronger. They both have a power of y, sure, otherwise we wouldn't be able to do anything. Yes. They're both multiples of 4 as well, yes. Yeah, so in this example, those things you said are all true, by the way, guys. They're actually both powers of 2 as well. In your power chart, you'll find they're both in that same row. 16 is 2 to the power of 4. And 8 is 2 to the power of 3. So I can replace 8 with 2 to the power of 3, and I can replace 16 with 2 to the power of 4. That's the only number that works, is 2 there. So yes, they're both divisible by 2. They both have a common factor of 8. They both have a common factor of 4. They're also both powers of 2. Okay? Not all numbers that divide by 8 are powers of 2. For example, actually that is maybe a false statement. No, that is a false statement. Every number that divides by 8 is in fact power. No, 24 is not. Okay? So if you had 24 to the power of y, 24 is divisible by 8, but it is not a power of 2. Okay, in any case, the reason I did this is I can now do power of a power, and I can write this as 12y plus 4, and I can write this as 2 to the power of 3y. Okay, and now I have the idea, and no matter how you solve exponential equations, this is what you want to get. One power equals another power. And in our example, the bases are the same, so we know the exponents must be the same as well. So 12y plus, or that's a 4. 12y plus 4 equals 3y, so bring the 3y over and we get 9y, bring the 4 over, we get negative 4. This is negative 4 ninths. Does that make sense? Okay. Slowly and a little bit harder. For example, 81 and 1 over 243. So our goal is still the same. We want to try to write both sides as powers of the same base. Now, I know it's 1 over 243, but let's just look at 243 and 81. Can they be written as powers of the same base? Basically, you're saying, are they on the same row? Yes. Good. So this is 81 is 3 to the power of 4. So now that becomes 3 to the power of 4 or 2x. If you want, you could do this. 1 over 3 to the power of 5. Yes. It's 3 to the negative 5. That's right. So 3 to the power of 5 is equal to, let's write this down next time. Yeah. 3 to the power of 5 is 243. So 3 to the power of negative 5 is 1 over 243. Sometimes I like to tell students, you could take your powers chart and you can make it a negative powers chart by changing all the exponents to negative. What would you have to do then with the chart after you changed all the exponents to negative? Yeah, all your answers for 1 over. Or the base. Yeah, all the answers would be 1 over. So then it's a negative powers chart. Okay? No, you can't do that, but just understand it. Power of a power, this is 3 to the power of 8x. When I say you can't do that, I'm saying you can't use that on your test. And now there we go. We have two powers that are equal. Their bases are the same, therefore their exponents must be the same. 8x equals negative 5, so you get x equals negative 5/8. These are slowly going to get more difficult. You ready for the next level? Let's see. These were level 1. Okay, like Mario level 1, Mario level 2. I think you went through like a warp whistle. You're on Mario level 7 now here, okay? Oh, don't do that. There's already an equal sign, so put an equal sign there. Actually, no, yeah, we'll go 5, level 5. What's that? We just skipped level 4. We went down to 2. There was 5, 6, 7. We chose to do 5. All right, 4 times 3 to the power of negative x equals 36. Sometimes it's helpful to look at this and notice what makes this one different than the other ones that we've seen. There's something there. It's not complicated. Yeah, you know. It's a negative variable, fine. Yeah. I think you're going to have trouble making 36 a power of 3, but there's also something else hanging out there. You see 4? There's a 4 hanging out there. There's a really easy way to get rid of that 4. Do you know what it is? Divide it out. So if you divide both sides by 4, then all of a sudden you make this look like all the other problems. You get 3 to the power of negative x equals 9. That's a pretty simple one. 9 is 3 squared. So therefore, negative x must equal 2, x equals negative 2. All right, now this one, here we got a little bit more work. Okay, I've got 9 to the power of x plus 4 divided by 27 to the power of x minus 1 equals 81. But thankfully, these are all nicely chosen problems, because what do you know about 9, 27, and 81? They're powers of 3. Now, if you're saying, hey, they're all divisible by 9, absolutely, they are all divisible by 9. That's fine. It just doesn't help us. The fact that they're all also powers of 3 helps us as well. Okay, every power of 3 bigger than 3 is going to be divisible by 9. In any case, so I'm going to replace them all as powers of 3. That's 3 to the power of 4. 9 is 3 squared, but it's now 3 squared to the power of x plus 4. And 27 is 3 cubed. That's now 3 cubed to the power of x minus 1. Power on a power gives us 3 to the power of 2x plus 8 divided by 3 to the power of 3x minus 3 equals 3 to the power of 4. So I took care of my power of powers there. Okay, just by multiplying. When you multiply, by the way, the power of power, be sure you distribute the 2. So you multiply the x by 2 and the 4 by 2. All right, what do you think I do next? So this is a power of 3 divided by a power of 3. So we can use our exponent laws to subtract, and we're going to get 3 to the power of negative x. Be careful here. This is positive 8, subtract negative 3. 8 subtract negative 3 is actually adding, so it gives us 11. We have plus 11 equals 3 to the power of 4. And now we've got that very special step where I have 2 powers that are equal. The base of the powers are the same. So if 3 to the power is something, if you do 3 to the power is something, and your friend does 3 to the power of something, and you get the same result, the power of somethings, the somethings had to be the same. You must have had the same exponent. So negative x plus 11 must equal 4. Bring the 11 over, or subtract 11 from both sides, you get negative x equals negative 7, x equals 7. Okay, and I've got one more for you to try, or for us to try. And this one, I think you'll find is quite a bit more difficult. 6 to the power of x plus 1 plus 6 to the power of x plus 2 equals 7. Yikes. I mean, we could look at this and start looking at the 6's. Like 7 and 6, they're not powers of anything. Okay, they don't even share any common factors. Like, do you see that the plus is really annoying? That there's like no exponent law here? It seems like we're really, really stuck. Anyone have any idea what we can do here? Yes. How are we going to break them down? So you can't do 3 times 2 because the exponent's glued here. I mean, you could do this, right? But this, I don't think you'll find that this is helpful. That's true, but I don't think it's helpful. All right, I'll give you a, go ahead. So the problem with that, and I mean, this isn't wrong, I just find that you're still stuck here. So that's true as well, but I think you're still stuck. There's no way to get rid of that 7. I mean, you can bring the 7 to the other side, but now we're just kind of going to go around in circles. It's a good idea. Generally speaking, when you're trying to solve an equation in math and you're not sure what to do, we always end up doing the same. There's one strategy that's often very, very helpful, regardless of the type of equation. You have an idea? You could, that's not necessarily helpful in this case, but sometimes it is. In this case, I wouldn't actually set it to 0. I don't think you generally want an exponential function set to 0. Yeah, it's factoring, just like with quadratics. Factoring is a very good strategy that works. You can actually factor the left side of this equation. Now imagine just imagine, it was something like, x squared plus x to the power of 4 equals 7. If you wanted to factor that, which wouldn't help you solve right away, you'd have a common factor of x squared, and you do this. Okay, that's what we're going to do here on this actual equation. I'm going to leave this as 7. What is the greatest common factor between 6 to the power of x plus 1 plus 6 to the power of x plus 2? So here the greatest common factor was x squared, basically the lowest exponent. So here it would be 6 to the power of x plus 1. So we can factor out a 6 to the power of x plus 1. As it turns out, as long as we factor out a 6 to the power of x, we can make the question work. When I do that, I'm now going to get 1, because 6 to the power of x plus 1 divided by 6 to the power of x plus 1 is 1. And I'm going to get 6 here, or 6 to the power of 1, if that helps. Think about why this works if you expand. 6 to the power of x plus 1 times 1 is 6 to the power of x plus 1. 6 to the power of x plus 1 times 6 is 6 to the power of x plus 2. You add the exponents. And look what happens now. 6 plus 1 is just 7. Ooh. Now, this is a convenient result. This question works out nicely because guess what I can do with 7? Divide it out. Very good. So if I divide both sides by 7, like so, then I'm going to end up with 6 to the power of x plus 1 equals 1. And we've taken this complicated equation, and we've now made it into a power equals something. And actually, I can write these as powers of the same base, because guess what? 1 is 6 to the power of what? 0. Anything to the power of 0 is 1. So 6 to the power of x plus 1 equals 6 to the power of 0. Therefore, x plus 1 equals 0, and x equals negative 1. There you go. Tricky question, yeah. But now you've seen it, so you'd be able to do it. All right, so I'm going to worksheet for some you to try. I've circled the ones that I think that you should try, so they're all fine to do. Let's give that to you right now.